Okay, so let's talk our way through elimination a little bit. So let me assume that I live in a world where I have a system of equations. So that system of equations, for instance, might look like 1x plus 3y equals 9, and 2x plus 4y equals 14. Okay, so I think that we could consider this as a matrix equation, right? So if I thought about this as a matrix equation, I would be thinking about the matrix 1, 3, 2, 4. Right? That's the coefficients here, times the vector x, y is equal to 9, 14. Cool with this? So in the interest of solving things like this, I'm going to consider solving things like this using the kind of approach called elimination. So in the elimination approach, what I want to do is I want to take my system that I start with and say, okay, I'm going to make a new system out of this thing. That system, I'm going to leave this first row alone. I'm going to select this first number, and I'm going to call that my pivot. It's kind of important that this number not be 0. If this number is 0, you rearrange the system, right? These are just two equations. They can be arranged in the other order. It doesn't matter at all. Okay. So, please note that that interchanges the rows of your matrix equation. But more on that later. For right now, we just assume this number is not 0 to start with. So I have a 1 there. I'd like to get rid of this 2x, right? So I think to myself, okay, I'm going to take this guy, and I'm going to multiply this row by something, and I'm going to add it to the second row. So that kind of operation I'm doing here, if you're familiar with this notation, is I'm making a second row 2, right? So the new row 2, and that new row 2 is going to be the old row 2 minus twice the old row 1. You guys see this? So my preferred method is to write minus 2 row 1 under here in a different color. So that's going to be minus 2x, right? And minus 6y and minus 18 here. And then I'm going to leave my first row alone. So I'm going to have 1x plus 3y equals 9. And then my second row, I'm going to add things. So the point was to get the x's to cancel. So I have 0 x's. And then I have minus 2 y's. And this is going to equal minus 4. You guys see this? Okay. Now this represents a different matrix equation. So this represents the matrix equation. Oops. That was a crappy spot to put a 1, Joe. 1, 3, 0, negative 2 times xy is equal to a different vector, 9, negative 4. So in the case that I started up here, I'm thinking this is a lot like an equation ax equals b. Then I did some stuff, right? So I eliminated a little bit. So that was here. I applied the idea of elimination, right? And I ended up with this new system that looks like ux equals c. So see, the x vector didn't change, but the matrix changed, and also the vector it's equal to changed. Does that make sense? I'm calling this u because this matrix is what's called upper triangular, meaning on the diagonal it has numbers, above the diagonal it has numbers, and below the diagonal it has zeros. So any matrix with zeros below the main, only zeros below the main diagonal, is called upper triangular. Put that in here. This is upper triangular matrix. Okay. In the case that I have several equations here, right, I may need to do some more elimination steps to get to an upper triangular matrix. So instead of one step here, I might have several. We'll talk a bit more about that later. For right now, I want to highlight what I've got at the end here. So let's see. So after I'm done with this, right, just a tiny bit of manipulation here, just a little bit, will get me to, well, that second equation actually tells me that y is 2. You guys see that? And then we can do what's called back substitution. Right, so we go look at our first equation, which says that x plus 3y is 9. Well, if y is 2, then this 3y part is 6. So that means that x has to be 3. Is that part recognizable, hopefully, from algebra class, I think? Okay, so this is kind of our idea of elimination. We picked a pivot, and then we zeroed out everything below it. In the case of a larger matrix, right, so, sorry, how about a 3 by 3 system? So in the case that we had 2x plus 3y plus 7z equals 8, and 3x plus 4y minus 8z equals 1, and 2x plus 8y minus 6z equals 23. It's entirely possible that I've set the system up badly. This may not work, right? But in this case, this would be my pivot, right? That would be my first pivot. And then my goal would be to zero out this 3 first, so that's my first target. This 2 next, that's my second target. Then my goal is I'm going to consider whatever's left here in this kind of middle position. That's going to be my next pivot. Then I'm going to zero out this guy. So this is going to be kind of my second pivot. And this would be my third target. Then this would be my last pivot, and I would be done. Right? So I would have an upper triangular case once all 3 of these were 0. Now, there might be some rearranging that you have to do. We'll get to that later. But for right now, I just need you to know, pick a pivot, zero out that whole column using multiples of the first row. You have to use multiples of the first row. Don't willy-nilly add these things together. If you use the third row, it'll get all jacked up. Just, yeah, first rows. And then in the end, once you've got that last pivot, then you can solve that last equation and back substitute the rest of the way out of this. Let's talk about what it looks like when it breaks. So if we happen to have a system that looked like 1x plus 2y is 7, and 2x plus 4y is 14, we would say, okay, so 1 is my pivot, so then my next step is going to be to eliminate out of the second row that 2, right? So that's going to be a step saying, all right, so the new row 2 is the old row 2 minus twice the old row 1. I don't know why I'm always doubling things. It's not always double. All right, so I'm going to write my minus 2 row 1 down here. So that's going to be minus 2x, minus 4y, and minus 14. Right? So in this case, after one elimination step, I'll be left with 1x plus 2y equals 7, and 0x plus 0y equals 0. Okay, now there's no information contained in that second row because that works for all x's and y's, right? So that means that my only information is contained in this first answer, or sorry, in this first equation. And in fact, in this case, the first equation is my answer. So this means that there are infinitely many solutions. And those solutions are of the form, well, if I take that first equation and rearrange it, right, I get x is 7 minus 2y. You might recognize this as being a line. If you don't recognize it as being a line, you might recognize that I'm going to have a solution, right, that's really a vector, right? So if I thought about my vector xy here, right, so if I thought about my original equations in terms of a matrix, right, so that would be the matrix 1, 2, 2, 4 times the vector xy. is equal to this vector 7, 14. And what I've found is there are infinitely many ways to get this to happen, right? In fact, this means that my solution vector looks like, well, it looks like x here, but what do I know about x? Well, I know x is 7 minus 2y. What do I know about y? Well, I don't know anything about y, so y could be anything. Y could be y for all I know, right? Some of the time we'll have choices for free variables. I'm going to tend to leave them. Some books like to sub a t in here. Doesn't matter too much to me. But in this case, that's my solution, right? This is really the vector x that solves this thing. So you could, either way, green or blue, either one of these describe the same line, right? So feel free to kind of fiddle around with this and convince yourself that that's the case. All right, the other way in which this could break, I'm just going to use this same system, except I'm going to change one thing. So I've got 1x plus 2y is 7, and 2x plus 4y, and in this case I'm going to write 15. Right, it's just a small change. I'm going to do that exact same elimination step, except now, once I've completed that elimination step, I'm going to have 1x plus 2y is 7, and I'm going to have 0x plus 0y is, well, in this case, I'm going to get 1. You guys see that? So in this case, there's no x's, so no x's and no y's add to 1. What x and y could I put in for this? There aren't any. So this is no solutions. What this means is that, yeah, there isn't a vector x, right? So if I thought about this in terms of my matrix, right? So if I thought about this as a matrix equation, this is the matrix 1, 2, 2, 4 times the vector xy. And I'm wondering, when is that equal to 7, 15? Well, as it turns out, there isn't one of these. Right? In other words, this 7, 15, it's just not in the range of 1, 2, 2, 4. This would be a case where my matrix here fails to be invertible. Right? You guys see that? Okay. You might notice, right, that the first row is half of the second row. You might, or sorry, I said column. I pointed at columns instead of rows. So the first column is half the second column. It's also true that the first row is half the second row, right? So this is a dependent set of vectors in here, which is part of the reason that this is happening to me. When the vectors are dependent, they tend to be either zero solutions or infinitely many. We'll get a little bit more into why as we go, but for right now, I just need you to know that there are two ways for this to break. In terms of the row picture, right, when we think about these in terms of lines, this one is saying that the infinitely many solutions are happening because these are the same line. Right, so that's this kind of picture where I have a line, and then I have a second copy of the exact same line. So when I ask where do they intersect all over the place. In fact, they intersect on the whole line, right? In this case, when I ask where does this line and this line intersect, well, I moved it just a little bit, right? I said, oh, it's just a little change. Well, oh, it is just a little change, except now they're parallel lines, so they don't have an intersection. I hope that makes some sense. So I have kind of all three cases highlighted here. In this case, right, I have two lines like this that actually intersect at a point, and that point is this x is 3 and y is 2. Down here I have two lines that intersect over the course of, well, really, I have one line that intersects itself everywhere, right? And then down here I have two parallel lines that never intersect. So these are the kind of consequences that you can have with elimination.